Alright, let's go. Number 10. The solar neutrino problem. Ray Davis wasn't hunting mysteries. He wanted to confirm what John Bacall had already worked out on paper, that the sun runs on fusion, hydrogen fusing into helium in the core, with neutrinos as the receipts of that reaction. Build a detector deep enough to shield from cosmic rays, count the neutrinos as they arrive, confirm the model. A verification job, a career-defining bit of bookkeeping. Bacall's standard solar model made a precise prediction. Around 7 to 9 SNU, solar neutrino units, should reach Earth from the proton-proton chain and the boron-8 branch. The sun burns, the neutrinos stream out at nearly the speed of light. They pass through the Earth barely noticing it's there. A small fraction interacts with chlorine atoms and converts them to argon. Count the argon atoms, confirm the flux. Davis found roughly 1/3. Not a calibration drift, not a rounding error, a structural absence. 2/3 of the sun's predicted neutrinos were simply not arriving. Ray Davis and his team at Brookhaven National Laboratory published in Physical Review Letters in 1968 that the home state chlorine detector, 615 tons of tetrachloroethylene, sitting 1,478 meters beneath South Dakota, was measuring roughly 2.56 SNU against a predicted 7.6. The deficit held through 25 years of continuous data collection. The first explanation was that the detector was broken. It wasn't. Galex in Italy and Sage in Russia, using gallium instead of chlorine, confirmed the deficit independently. The second was that Bacall's solar model was wrong. It wasn't. Heliosismology mapped the sun's interior structure and matched the model to within 1%. The third was that something was absorbing neutrinos en route from the sun. Nothing in known physics could absorb them. The fourth was statistical fluctuation. 25 years of data killed that. The eventual resolution, confirmed by the Sudbury Neutrino Observatory under Arthur McDonald in 2001, did not save the standard model. It broke it. The neutrinos hadn't gone missing. They had changed identity mid-flight from the sun to the Earth, which meant they had mass, which meant the foundational particle physics of the 20th century was incomplete. And even after oscillation is factored in, the count still doesn't perfectly match. Something remains in the gap. That opens the door to something worse. Number 9. Neutrino oscillation itself. Bruno Pontecorvo wasn't trying to overturn anything. In 1957, working at the Joint Institute for Nuclear Research in Dubna, he was extending Gell-Mann and Pace's work on neutral kaon mixing and asked whether a similar oscillation might apply to neutrinos. It was a theoretical curiosity. The standard model, still being assembled, treated neutrinos as strictly massless, 3 flavors, 3 lanes, no crossing over. Under the original standard model as formalized by Glashow, Weinberg, and Salam, a neutrino produced as an electron neutrino must remain an electron neutrino. Zero mass means zero rest frame proper time, which means no clock, which means no oscillation. The math is airtight. If neutrinos have no mass, they cannot change flavor, ever. They change flavor, repeatedly. In detectors around the world, the rule is not bent, it is broken. Yoichiro Suzuki and the Super Kamiokande collaboration, published in Physical Review Letters in 1998, the definitive evidence, atmospheric muon neutrinos disappearing at a rate that depended on the distance traveled. Arthur McDonald's SNO group in Sudbury, Ontario, confirmed the solar case in 2001 in Physical Review Letters. Both received the 2015 Nobel Prize. The result is unambiguous. The immediate patch was to give neutrinos a small mass by hand, but the standard model's Higgs mechanism generates fermion masses through Yukawa couplings that require right-handed partners, and right-handed neutrinos have never been observed. A second patch, the seesaw mechanism, invokes hypothetical particles at energies no accelerator can reach. A third, Dirac versus Majorana nature, remains undecided after 30 years of searches. Every fix requires physics beyond the model the fix is meant to preserve. The standard model, the most tested framework in the history of science, has a hole in it. The hole is a particle we've detected quadrillions of times. If a particle this ubiquitous violates the theory, what else does? The next anomaly is worse because it might not be about neutrinos at all. Number 8. The MiniBooNE Excess. Fermilab's MiniBooNE experiment was built to be boring. The team, led by Janet Conrad and Bill Lewis, wanted to test a strange result from an older experiment in New Mexico, the LSND Anomaly, using a completely different technique. Send a beam of muon neutrinos through 800 tons of mineral oil. Count how many arrive as electron neutrinos. If LSND was a fluke, the count would sit at background. Job done. Standard 3-neutrino oscillation, over the short baseline MiniBooNE used, predicts almost no muon to electron neutrino conversion. The expected signal was essentially indistinguishable from detector noise. A null result would end a 15-year controversy and let the field move on. MiniBooNE saw the excess, not once, not twice, continuously. Low-energy electron-like events piling up above prediction, refusing to disappear across 17 years of running. Aguilar Aralo and the MiniBooNE collaboration published in Physical Review Letters in 2018 that they had observed 460.5 excess electron-like events above prediction, at a statistical significance of 4.8 sigma. Combined with LSND, the combined significance reached 6.1 sigma, well past the discovery threshold in every field of physics that isn't this one. The first explanation was background from misidentified photons. Refined analysis reduced, but didn't eliminate the excess. The second was neutrinos from unexpected sources in the beam. The NUMI beam data ruled that out. The third was a fourth sterile neutrino, a particle that doesn't interact except through gravity and mixing. MicroBooNE, a follow-up at Fermilab designed specifically to test this, published in Physical Review Letters in 2022 and found no matching electron neutrino signal. The sterile explanation weakened, the excess did not. Something is producing extra events in a detector we understand at the percent level. We do not know what. If it isn't a new particle, and it isn't a background, what is it? The excess didn't appear from nowhere. It had a predecessor. Number 7. The LSND Anomaly. The liquid scintillator neutrino detector at Los Alamos wasn't looking for new physics. In the early 1990s, Bill Lewis and his collaborators were measuring standard neutrino oscillation parameters over short distances, a calibration project essentially meant to nail down mixing angles before the field moved to bigger detectors. Fill a tank with 167 tons of mineral oil doped with scintillator. Aim a proton beam at a target upstream. Watch for the flashes. Over such a short baseline, 30 meters, the 3 known neutrino flavors, mixing at their measured rates, predict a negligible number of antineutrino conversions. A handful of events, well within statistical noise. The experiment was expected to see nothing interesting and confirm known oscillation parameters as a byproduct. They saw a clear excess of electron antineutrinos, small in number, statistically undeniable, a signal where the theory said there could be none. Athanasopoulos and the LSND collaboration published in Physical Review Letters in 1996 that they had observed 51.8 plus or minus 18.7 events above background, at 3.8 sigma significance. Refined analysis in 2001 in Physical Review D, published by A. Aguilar and colleagues, tightened the significance to 3.8 sigma with 87.9 excess events. The result held under every reanalysis. The first suggestion was cosmic ray contamination, ruled out by veto systems. The second was neutron backgrounds from the beam dump, ruled out by timing cuts. The third was 3-neutrino oscillation with unusual parameters, ruled out by Camland and Super Cameo Cande, which mapped the mixing angles precisely and found no match. The fourth was a sterile neutrino at around 1 eV mass, the only surviving hypothesis, still unconfirmed 30 years later. MiniBooNE was built specifically to check whether LSND was a fluke or something real. It confirmed the anomaly and made it worse. 2 independent experiments, 2 decades apart, seeing the same forbidden signal. What are they detecting? The next one comes from the coldest place on Earth and points at things that shouldn't exist. Number 6. IceCube's high-energy flux mismatch. The IceCube Neutrino Observatory was drilled into the Antarctic ice cap under Francis Halson's leadership as a general-purpose cosmic neutrino telescope. The team wanted to identify the astrophysical sources, active galactic nuclei, gamma-ray bursts, supernova remnants that produce the highest energy neutrinos in the universe. Instrument a cubic kilometer of ice. Wait for flashes. Trace them back to their origins. Standard models of high-energy cosmic ray production predicted a specific spectrum of astrophysical neutrinos arriving at Earth. The energy distribution should follow the sources, a power law with a well-defined index, cutting off where the underlying accelerators run out of steam. Match the neutrino spectrum to the gamma-ray sky, and the picture closes. The spectrum doesn't match. IceCube sees high-energy neutrinos in numbers and at energies that don't correspond to the identified astrophysical sources on the gamma-ray sky. Artson and the IceCube collaboration published in Science in 2013 the first evidence of a high-energy astrophysical neutrino flux, followed in 2020 in Physical Review Letters by refined measurements showing an unbroken power law spectrum from around 60 TeV up to several PeV, with a spectral index softer than most predicted source models allow. The first candidate was gamma-ray bursts. Dedicated searches by IceCube found essentially no correlation. GRBs cannot dominate the flux. The second was active galactic nuclei. Only one blazar, TXS 0506 plus 056, has been linked to a single neutrino event in a 2018 Science paper. The third was starburst galaxies. Their gamma-ray output is insufficient. The fourth was hidden cosmic accelerators, sources opaque to gamma rays but transparent to neutrinos. This remains speculation without a confirmed detection. The highest energy particles ever detected arrive from directions we cannot resolve, produced by objects we cannot identify. The universe is emitting a signal we can measure but not source. What is out there? The problem sharpens when you look at what we still don't know about the particle itself. Number 5. The mass hierarchy problem. Oscillation experiments over the last 3 decades have been extraordinarily productive. Groups at Super Kamiokande, SNO, Comland, Diabae, Reno, and Double Choose measured the mass-squared differences between neutrino flavors and pinned down the mixing angles to a few percent. The workhorse job was straightforward. Measure the parameters, feed them into the theory, close the chapter. The theory requires knowing the ordering of the 3 neutrino masses. There are 2 possibilities. Normal ordering. The 2 lightest states are close together, with the heaviest well above them. Or inverted ordering. The 2 closest states sit at the top, with the lightest well below. Every calculation involving neutrinos in cosmology and particle physics depends on knowing which. We still don't know. After 60 years of neutrino physics, one of the most basic properties of a well-studied particle remains undetermined. The T2K collaboration in Japan, the NOVA collaboration at Fermilab, and Super Kamiokande have all attempted to distinguish the 2 orderings. The combined data slightly favors normal ordering. A 2023 global fit by the NewFit collaboration in the Journal of High Energy Physics gives roughly 2.5 sigma preference, but this is nowhere near a discovery. Precise long baseline experiments should have resolved it. They haven't. The sensitivity depends on the unknown CP violating phase, which is itself unresolved. Reactor experiments should have resolved it. They haven't. The mass splitting they measure is nearly independent of ordering. Cosmological constraints from the cosmic microwave background should have bounded the sum of masses tightly enough to force an answer. They haven't. The current Planck bounds are consistent with both orderings. Every experiment designed to answer this question has failed to answer it, and the reasons for failure are different in each case. A property of matter that composes trillions of particles passing through your body every second, unknown after 6 decades of dedicated work. If we can't rank the masses of a particle we've caught quadrillions of times, what does that say about the rest of the model? The confusion deepens when the theorists' own numbers stop matching the reactors. Number 4. The Reactor Neutrino Anomaly. The measurement of reactor antineutrino flux was supposed to be one of the most reliable numbers in particle physics. Nuclear reactors produce electron antineutrinos as a byproduct of fission, at rates calculable from well-measured beta decay spectra of the fission fragments. Groups at Buji, Choose, and later Diabae were doing routine calibration and precision oscillation measurements at short baselines, where oscillation effects should be small. The prediction was a specific antineutrino flux, calculable to within about 2%, based on nuclear data for uranium-235, uranium-238, plutonium-239, and plutonium-241. Short baseline detectors should measure that flux almost exactly, since standard oscillation over meters is negligible for reactor energies. Reanalysis of the world's short baseline reactor data in 2011 found a persistent deficit. Detectors were measuring about 6% fewer antineutrinos than the models predicted. The deficit was small but systematic, visible across independent experiments at independent reactors. Mention and collaborators published in Physical Review D in 2011 a global reanalysis showing a measured to predicted ratio of 0.943 plus or minus 0.023, a 2.5 sigma deficit. Follow-up work by the Dia-Bay collaboration in Physical Review Letters in 2016 refined the numbers and found that the deficit tracked with uranium-235 more strongly than with plutonium, complicating the picture further. The first explanation was sterile neutrinos at the EV scale, the same suspects behind LSND and MiniBooNE. Very short baseline experiments, including Prospect and Stereo, published in 2020 and 2021 in Physical Review Letters, largely ruled out this specific parameter space. The second was that the nuclear reactor flux calculations were wrong. This is now the leading explanation, but the models used were the same ones that had been trusted for decades. The third was detector-specific systematics. Multiple independent detectors show the same effect. Either a well-established nuclear physics calculation is wrong at the 6% level, or a particle we cannot find is intercepting the missing signal. Which is the more comfortable failure? The uncertainty leaks into a much larger question about matter itself. Number 3. CP violation in neutrino oscillation. The T2K experiment in Japan, led originally by Koichiro Nishikawa, was designed to measure oscillation parameters precisely by shooting a muon neutrino beam from J-Park to the Super Kamiokande detector, 295 kilometers away. The specific target was theta 13, the last unmeasured mixing angle, plus a first look at whether neutrinos and antineutrinos oscillate at different rates. Standard precision work with a bonus objective. If the laws of physics treated matter and antimatter identically, neutrinos and antineutrinos should oscillate at exactly the same rate. This is CP symmetry. Under CP invariance, the oscillation probability from muon neutrino to electron neutrino must equal the oscillation probability from muon antineutrino to electron antineutrino. Any deviation is a direct violation. T2K found deviation. Neutrinos oscillating faster than antineutrinos. A sign, not a rounding error. Abe and the T2K collaboration published in Nature in 2020 evidence that the CP violating phase delta CP lies near minus pi over 2, with 3 sigma confidence excluding the CP conserving values of 0 and pi. The result was called the first direct hint of CP violation in the lepton sector, a category of experiment that had produced only null results for decades. The first attempt to reconcile this was statistical. With limited events, the signal could shift. More data over 3 additional years narrowed but did not eliminate it. The second was systematic uncertainty in neutrino cross-sections, which are notoriously poorly measured. Independent measurements at Minerva and Nova have improved but not resolved this. The third was that T2K's result would fade against Nova's data. Nova in Physical Review D in 2022 gave a slightly different but overlapping preference. The tension persists. If leptonic CP violation is real, it may be part of the answer to why the universe contains anything at all rather than a bath of annihilating photons, which is exactly the next question, on a larger scale. Number 2. The matter-antimatter asymmetry problem. Andrei Sakharov wasn't building an experiment. In 1967, working in the Soviet Union, he wrote a 3-page paper in Jet P letters listing the conditions any theory would need to satisfy to explain why the observable universe contains matter and essentially no antimatter. Baryon number violation, C and CP violation, departure from thermal equilibrium. A framework, not a mechanism. The standard cosmological picture requires the early universe to have started with essentially equal amounts of matter and antimatter, which should have annihilated completely into photons. What remains today should be a universe of pure light. The observed ratio of baryons to photons is about 1 to a billion, a tiny leftover of matter that shouldn't be there. That tiny leftover is everything. Every galaxy, every star, every atom in your body, all of it is a rounding error in a cosmic annihilation that should have been total. Fukugita and Yanagita proposed in Physics Letters B in 1986 the leptogenesis mechanism, heavy right-handed neutrinos in the early universe decaying asymmetrically into leptons versus antileptons, with the asymmetry later converted to baryons through sphaleron processes. The mechanism requires CP violation in the neutrino sector. The T2K hints support this. Direct confirmation requires detecting the heavy right-handed neutrinos, which sit at masses ranging up to 10 to the 15 GeV, far beyond any accelerator ever proposed. The first alternative was electroweak baryogenesis, using the Higgs. The measured Higgs mass makes this quantitatively insufficient. The second was gut-scale baryogenesis. Proton decay searches have ruled out most of the required grand unified theories. The third was that we live in a rare matter-dominated patch of a larger balanced universe. No boundaries between matter and antimatter regions have ever been observed. Every explanation for your existence requires physics we cannot test. You are the residue of a war fought before the first second, decided by rules no one has written down. The list closes with the particle that would explain half of it. Number 1. The unresolved sterile neutrino. Physicists working on LSND, MiniBooNE, the gallium calibration experiments, the reactor anomaly, and cosmological large-scale structure did not set out to invent a new particle. Each group was doing careful, targeted work, precision measurements at specific energies and baselines, meant to close the books on their respective questions. The sterile neutrino emerged as the simplest common explanation for a family of independent anomalies that otherwise share nothing. A sterile neutrino would be a fourth kind of neutrino that does not interact via the weak force. It would mix with the three known flavors, causing oscillations at a new mass scale, typically around 1 electron volt, that would appear in short baseline experiments as anomalous appearance or disappearance signals. It would explain LSND, MiniBooNE, the reactor deficit, and the gallium anomaly at once. A single elegant patch. 2 decades of dedicated hunting, no direct detection. The MicroBooNE collaboration at Fermilab published a series of papers in Physical Review Letters in 2022, finding no signal consistent with the MiniBooNE sterile hypothesis in the electron-neutrino channel. The Prospect collaboration at Oak Ridge, in Physical Review D in 2020, ruled out large portions of the reactor sterile parameter space. The Best experiment in Russia, published in Physical Review Letters in 2022, actually strengthened the gallium anomaly with a 4 sigma deficit, pushing the sterile hypothesis in the opposite direction. The first attempt to reconcile all data with a single sterile neutrino has failed. No single mass and mixing works for every anomaly simultaneously. The second was multiple sterile neutrinos. This introduces free parameters faster than data can constrain them. The third was that the anomalies have independent causes and only look similar. This would require several unrelated unknown physics effects to appear at once. The fourth was that the anomalies are all systematic errors. Multiple independent detectors, techniques, and decades of work make this increasingly hard to believe. A particle that would tie together the loose ends of neutrino physics is either hiding from every detector built to find it, or it does not exist and the anomalies are pointing at something we haven't imagined yet. Trillions of neutrinos pass through your body while you watch this. Some fraction of them may not have been the particles we think they are. Every entry on this list lives inside the standard model, not at its speculative edges, but at its most tested core. Neutrinos are the second most abundant particle in the universe after photons. We have detected them for 6 decades, in mines, in ice, under mountains, from reactors, from the sun, from supernova, from the atmosphere. And on almost every axis we can measure them. Flavor, mass, oscillation rate, flux, symmetry, asymmetry, they refuse to match the theory that predicts them. The universe is not confused. Our best physics is. If you want to see more videos like this, click the video on screen now.